Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, first, let's introduce the page fault rate. Okay, during the execution of a process, a reference string will be created for the process. It shows the list of page references. Suppose T is the number of page references. And during this time period, there are F page fault. So F is the number of page faults during this time period. Now we define the page fault rate as P, which is page fault rate, as F divided by T. Okay. So since T is the total number of page references and the F are the references which cause the page fault. So F is definitely smaller than P. So F is definitely smaller than T, right? So P is between 0 and 1. Now 0 means if P is 0, that means T is 0. So that means there's no page references. Okay. Now if P is 1, that means F equals T. So that means every page references cause the page fault. So that's the worst scenario. Okay. So we also introduce another concept, which is the effective access time. Okay. So effective access time is the average time to access memory in the presence of page faults. Okay. So let's define the effective time as E. Okay. So E will be calculated using this formula. 1 minus P, P is the page fault rate, times M plus P times S, it's the capital S. Okay, now what is M? M is the time to access physical memory. Because, every time when you have a page reference, you're going to access the page physical memory. Okay, and S is the time to process a page fault. Okay, S is the time to process page fault. Now, when page fault happens, the time is going to be much longer, because when page fault happens, so that means we need to, copy the pages into the hard disk space and load the new page from the hard disk, because when page fault happens, so that it means that the page we try to execute is not in the physical memory. So it is actually in the virtual memory space, which is in the hard disk space. So you have to copy that page from the virtual memory space, which is in the hard disk, into the physical memory. And then before we do this, you have to, if the page is referenced, which is the current page in the memory is referenced, then you have to copy the page back to the hard disk, back to the virtual memory space. And then you copy the page to be executed into the physical memory. So moving the data from hard disk into the memory, that's very costly. Okay, so that's why the time to process a page fault is much, much bigger than M, which is the time to access the physical memory. Okay, so let's talk about the overhead of page fault using the example here. Now, suppose a memory reference takes M units of time, and T is the total number of memory references. So executing T memory references without any page faults takes T times M, right? T is the total number of page memory references. M is the time for each memory references. So that's the ideal case. Now suppose we have F page faults. So we have certain number of page faults. The number is F. And each page fault takes S time units. So the total number of time spent on page faults is F times S. Okay, so that's F times S. Now that's additional. Okay. Of course, the total amount of time on page fault are scattered all over the places. So now the hope is that that's the total amount of time for page fault, and that's the overhead, right? Now we hope the overhead, which is F times S, so the page fault, the total amount of time for page fault, is only 10% or less over the total amount of time for the memory reference. Okay. So that's F times S, T times M. So we hope that's less than 10%. Okay. Now, if we move the S to the other side, move the M to the other side, we got F over T less than M divided by time times the S. Now suppose M is 100 nanosecond. So that's 1/1,000,000 of a second, or 1/1,000,000th of the second, 1/1,000,000th of the second. Okay. So now S, the page fault time, is 10 millisecond. So that's 1,000th of a second. So this is actually 10 million. Okay. Nanosecond. Okay. Or 10 to the 7 nanosecond. Now that's 10 square nanosecond. Now suppose M is 100 nanosecond and S is 10 millisecond, which is 10 to the 7 nanoseconds. So we'll replace the M with 10 square. We'll replace S with 10 to the 7. Now we got 1 over 1,000,000. Now what does that mean? So that means the F divided by T, which is the page fault rate, should be less than 1 out of a million. In another word, so the page fault rate must not exceed 1 page fault per 1,000,000 memory operations. So we only allow 1 page fault for every 1,000,000 memory references. If we can do this, then we can control the total page fault overhead within 10%. Now, in the previous slide, we discussed the page fault rate. And we know that when the page fault rate increases, the page fault overhead increases as well. So now the load control we are going to discuss in this slide is to try to find the balance for this. So load control is the activity of determining how many processes should be running concurrently at any given time to maximize the overall system performance. When the number of processes increase, so are the number of pages, right? And when number of pages increases, then the chance for the page fault also increase. Okay. Now, if the number of page fault increase to the point that most of the time the operating system is going to spend on moving the pages between memory and the disk. In another word, so the page fault, reaches certain number, so that most of the time the CPU is spent on the page fault. Okay, so that's called thrashing. Okay, so thrashing is an execution state during which most of the time spent on moving pages between one memory and disk. Okay, why does this happen? That's actually the page fault, right? Page fault is basically the time spent on moving the pages between the memory, the virtual memory, which is the disk space, and the physical memory. Okay, and so while the CPU is mostly idle and not process any real progress. Okay, now as we mentioned, that the thrashing occurs when too many processes are sharing memory concurrently and no process has enough pages to operate without frequent page faults. So eventually, all the CPU times are spent on the page fault instead of doing meaningful job. That's called thrashing. Okay. Now this diagram basically shows the relationship between the CPU utilization and the number of concurrent process. As you know, that the number of concurrent process is small, then the CPU utilization is also small, right? When the number of process increase, number of concurrent process increase, the CPU utilization increase. Okay, increase. But the rate is slowing down. Now there's a point, okay, when L equals S, where L is the mean time between page faults, and S is the time it takes to service each page fault. When it's time to reach that equality, it reaches the peak. Okay, so that's a peak for the CPU utilization. Now, if you keep increase the number of concurrent processes, then the CPU utilization start to fall down, because that after you pass that point, okay, so that means the CPU spend more times doing the page faults. So we basically spend more times moving the pages from the memory to the disk space, to the virtual memory space. And now eventually you're going to reach the point where the CPU is pretty much doing nothing. That's the thrashing. Okay. That's all for module 7. Thank you.